Oh, there's Demi. Hello, Demi. Okay, let me turn my thing on here. So I've decided to have the test on Tuesday. So it will be, I don't know if I told you that or not, but okay, so the test is Tuesday. It's Chapter 1 plus the first 2 sections of Chapter 2, which we'll finish the second section here in about 10 minutes. Then we'll move on to Section 3, but that will not be on the test. What I will do is I will post a review video before the weekend so you can watch that before Tuesday. And basically what I do is I go through the tests and I talk about, I don't work the exact problems, but I work ones that are similar to them so you know exactly what's on the test. You can bring in one sheet of paper with notes of any kind that you want to have on there. So I'm not into memorizing stuff because I found out that even people, when they memorize stuff, they forget it about 6 months later anyway. So I found out that a lot of people who sent me their projects, the first part of the project, for some reason it's only sending me the data, not the graph. So I'll probably send out an email asking you to either send it as a PDF file. It works on the second one, so it's not that you can't send things with multiple sheets, because the second one with the data and then the attached graph worked, but the first one didn't, and I sent it to myself. I did it and I sent it to myself and it didn't work for me either, so it's not something, it's not particular to you. So you won't have to redo anything except you just have to go back in and send it to me again. So I'll let you know. I have a record of when you sent it to me, so you know, it's not like you're going to be late. So I read this real interesting article. I still haven't figured out what I think about it. It was about this guy. He's probably my age, maybe somewhat younger. And he went to a school, I think it was a high school in somewhere in the Midwest, where they didn't have grades and they pretty much, you know, there was no standardized testing, and they got to choose what they wanted to learn. It was kind of very, you know, hippie-ish kind of thing. And so he ended up thinking about when, you know, when he's older, he says, you know, I kind of miss some of the things that go along with normal high schools, whatever those are, you know, sports. I'm thinking they had a sports team, other things. And then, so he, as part of writing a book, he ended up substitute teaching for like a month or two. It wasn't that extent. It made it sound like he did it for a long, long time, but he only did it for, it was like 20 days worth of substituting, which is not that much. And he did from elementary through high school. And it was his observations about that. And ultimately he said, I was glad I got to go to the school that I got to go to. Because he was saying that normal education is mind-numbing, which was kind of interesting. And I was thinking about this class for you guys, because you know you're probably not math people, so you're not super excited about this kind of stuff. So you have to do it. But I was trying to figure out. You know, I teach calculus, which to be an engineer or a physicist or whatever, you need to know calculus. It's not like something that you can, and you got to do all this stuff. But for people who don't go into those kinds of things, it makes you think about, you know, what do you really get out of a high school education? What that's actually useful or not? It's an interesting pondering thought. So I was trying to think about that. Anyway, we still got to do this anyway. There used to be a person who ran the Achievement Center probably about 5 or 6 years ago, and she would always ask me, you know, what's the difference between watching a video of somebody giving a lecture versus having class? If all you get out of class is just sitting there and you could just get as much out of watching a video, then why do we do it this way? So she always thought it's easier with physics or something like that to to say, yeah, you couldn't do this in a video. Seeing it actually in person or talking to the person next to you about how you're solving a problem is important. But anyway. So let's finish up section 2 here. So we were talking about whether this was a subset, a proper subset of this set. And we said it was both because it's a subset because each element in this set is an element in this second set. It's a proper subset because they're not equal to each other. Whereas this one was this is a subset of this, but it's not a proper subset because it is equal. These two are equal to each other. Even though they aren't in the same order, they do have the same elements. Okay, so that's kind of, and we did that, something like that is on the test for sure. It's also like this is on the test. So here's another one, problems 21 through 40, so you'll have other ones too within this grouping. So you have a universal set which consists of the small case letters A through G. Set A is A and E. Set B is such, C, D. And so they're going to ask you questions about whether the statements are true or not. So you have to understand what this terminology means. So remember this C with a C-ish looking thing with an underline means subset. So this means not subset. So the question is this a true statement? D is not a subset of B. So we look at D and we ask, is D a subset of B? So is every element, so really you have to ask, is it a subset, and then answer the question, because it's harder to think of it as not a subset. It's easy to think of it, is it a subset? If it's a subset, then it can't be not a subset, right? But the opposite can't be true. So I'm going to look at it from a subset perspective. So is D a subset of B? Well, I look for D. Is D is in this one? Is it in this one? No. G is E. Is E in this one? Well, we could quit at that point, right? Because once you have proven that every element in set D is not in B, then you can just say it's not a subset. So even though E is in both of them, the fact that D is in set D and not in set B, then we can say it's not a subset, and therefore this statement is true. D is not a subset of B. So that's, all right, let's look at another one. So again, I'm going to answer this question not by answering this question straight ahead. I'm going to answer the question, is A a subset of B? And in that case, subsets, every element in set A has to be in set B. So we do the same thing. A, small case A is in A and in B, and small case E is in both A and B. So A is a subset of B. So you could say A is a subset of B, therefore this is false. So we'll say is false. Up here, what I did was I said the question I asked is D a subset of B, and the answer was no, and therefore it's not a subset. So that was kind of more simple. Okay, so that's how you kind of think about these things. So let me pick another one. One that's an affirmative. I'm making this up, so this is not in the book. This is N1, Nicholson 1. So A is a subset, let me think about this, is a subset of the universal set. So is A subset of the universal set? So I'll ask you guys for that one. Is that a true statement? Yes, yeah. So just compare set A with set U. Well, just by its nature, U contains everything. So all of those, A is a subset. So that is a true statement. That's what they're looking for. That's a true statement. So we'll say that's true. How about another one that involves is a subset? So if I said, is the statement, is D a subset of A? So the affirmative ones are kind of easy to answer. You just answer. You always want to answer the question, is something a subset of something else? And then you can answer the true or false question after that. So is D a subset of A? Yep. So the answer is false. It's not. So we answered this question by putting in false. Let's see if there's another one that might be. Is C, let's say C is not a subset of B. Is that a true or false statement? So again, what you do when you have the negatives of, you ask the question, is C a subset of B? So is C a subset of B? And the answer is, Jennifer's nodding her head, and it is, because B is in, small case B is in both sets. Small case F is in both sets. Small case G is in both sets. So C is a subset of B, so therefore that statement is false, right? Okay, onward. The last thing in this section, I think. So the question, one question comes up, and this actually comes up in probability in the second semester. You'll see why when we get there. But there's actually a formula that tells us how many possible subsets there are for a certain size original set, including the set itself. Remember, we're talking about regular subsets. Proper subsets, it's all the subsets except the one that's equal to the original set. That's why it's 2 to the n minus 1. N is the number of elements in the set. So let me just give an example of a fairly small set, so we don't have to do this too many times. But if I were to say this is set A, set A consists of the letters F, G, and H, the different instead of A, B, and C. The question is, what are the possible subsets of A? Question mark. So I'm just going to list them. So the set itself is a subset. And that's the only 3-element subset that we can have, because if we change the order, it's still the same set. So in this case, this is the only 3-element subset. Then you look at 2-element subsets. So what you do is you take like 2 of them here. You can take the first and the second, the first and third, the second and the third. Those are the 3 choices. So you take F, comma, G. I'll put a comma here. Then you can do F, comma, H. So you do the first and the last. And you do the second and third. Okay. Again, because G, comma, F is the same as F, comma, G, we don't repeat it. So those are the 3 possible 2-element subsets of this set. Then you have single-element subsets. Well, there's only one way we can do each one of those. You just take each element and put it into a separate set. So there are 3 1-element subsets of the original set. And then finally there is the null set. So the null set is the set with nothing in it. So we can either write that as this, or we can use the little symbol like that. That's null set. So if we count those, we get how many? Don't double count the last one. So what's the number? How many sets? How many subsets are there? You guys can count. So tell me. 8. So there's 8. So you got 4 on the top row, and then you have 4 on the bottom row. So in this particular case, we have 8 subsets. So the formula says the number of subsets of a set with n elements. In this case, n is equal to 3. It has 3 elements. And so what is the number of possible subsets? Question mark. Well, we could count these, but we can use the formula. It's just 2 to the n, where n is equal to 3. 2 to the third power is 2 times 2 times 2, which is 8, which agrees with what we got there. Okay. So for 3-element subsets, you know, it saves a little time. It's not that huge. If you had a 5-element subset, then you're starting to get a lot of subsets. You'd have 2 to the 5th power, which would be 32. I would want to have to list those if I was asked the question of how many subsets. So there'll be a question on the test asking you this question, and all you have to do is count the number of elements. I'm not going to say n equals 3, plug it in the formula. I'm at least going to say, here's the set. You're going to count the number of elements in the set, and then you're going to use the formula, which is 2 to the n power, whatever n is. So if I said, here's set B, and it consists of A, comma B, comma C, comma D, comma E, comma F, and I ask the question, how many subsets? I'd probably write in how many possible subsets, but I'm lazy right now. So what you would do is you'd say, okay, 1, 2, 3, 4, 5, 6. So n equals 6. I can count. That's good. And so the possible number of subsets is going to be 2 to the 6th power, which if you have a calculator that does powers, you can do it, or you can just multiply out 2 6 times, which is 64. The little mental math thing here. I still can't remember off the top of my head 2 to the 6th, 2 to the 7th, what those are, so I still have to multiply them out. And when I looked at this, instead of going 2 times 2 is 4, times 2 is 8, times 2 is 16, I looked and I said, oh, there's an even number. There's 3 2's here and there's 3 2's there. And I do remember what 2 cubed is. At least I remember that. So I said, oh, the first half's 8 and the second half's 8. So 8 times 8 is 64, which I could do quicker. That's what my thought process was. Okay, and then if I asked you how many proper subsets, then all you have to do is subtract 1. So the answer would be 2 to the 6th minus 1, which is 63. So in probability language, which we'll get into the second semester, which you'll get into either you take this class or you take Mr. Pell's class, they're called combinations sometimes. When you have order's not important. It's not exactly combinations, but sort of combinations. Okay. And this actually is kind of that example. So this is, it says, this is problem, oh, here it is, 57 through 62. So we have, how many people? We have 5 people. And it says they're going to meet in the hospitality suite. Each person is designated by a letter. So Amy's A and Bruce is B. List all the possible sets of this group in which the given number of them can gather. So what they're asking is, they're asking for subsets. Our set is all 5 people. But you can group those 5 people in smaller groupings. You can have 5 people, 4 people, 3 people, 2 people, 1 person, 0 people. And so they're not asking for the number, they're actually asking us to write all these out, I think. List all of the possible sets of this group. Okay. So the way it works is just like we did before, except it's with 5. So in this case, with 5 people, we would have A, comma B, comma C, comma D, comma E. So that would be, there's one 5-person group. Then you could do 4-person groups, and you'd have A, comma B, comma C, comma D. You would have A, comma B, comma C, comma E. Then you could have, what am I going to do here? You could have, so those are the 2 ways you can have A in there. So you just flip around. Well, is that true or not? Anyway, let's just think about this. We could do B, comma C, comma D, comma E. Yeah, I think there's only 3 ways you can do that. Let's skip the head one here. We'll do the easy ones here. 1 person, no, actually I think I have 2 more I have to do there. So the 1-person groups are pretty easy to do. You just put each one separately. Wouldn't be a very exciting meeting by yourself. 1 is the loneliest number. Anybody know that song? Who knows? Who sang that? 1 is the loneliest number that you'll ever know. 2 can be as bad as 1. It's the loneliest number since the number 1. Okay. It was Three Dog Night. That was the original. Anybody ever heard of Three Dog Night? That's the early 70s, I think. Okay. So those are the 1-person groups. This is the 0-person group. And the reason I knew that I needed 2 more is because these kind of tend to be symmetric. So there's one 5-person group, there's 1 0-person groups. And so I knew that if there are 5 1-person groups, they have to be 5 4-person groups. 2-people groups. So then you have A and B. You have A and C. You have A and D. You have A and E. Then you have B and C. You have, I'm going to have to add a page because I'm running out of space here. Then you have B and D. You have B and E. Then you have, let's go down here. How many have I got so far? 7. Turns out I need 3 more. So you have C and D. And you have C and E. And you have you have D and E. So there are 10 of those. So 10 of those. There are 5 of those. There should be 5 of these, which I haven't got them yet. And so you can see it's actually easier. Sometimes it's hard to use the brain power here to figure out all these different combinations. What I did was I started with A, and then I took every following letter. Then when I get to B, I don't go back and do BA because I've already got that. So BA is the same as AB. So I've got 4 of the ones that involve A's initially. Then I go the B's, there's 3 of those, B, C, B, D, B, E. There's also BA, but I've already written that down. Then you go to C, there are 2 of those because I've already got CA, CB. Those are over here, which were these 2. Well, they're over there. So you get 2 of those, and then you get one final one that you haven't covered already. Because I've got all the other ones. I've got AE, I've got BE, I've got CE, and D. The only one I don't have is DE. Turns out there's 10. So the same thing here. There should be 10 with 3 people. And I'm not going to work them all out. I'm just going to show you a few, and then you'll have to believe me. So that's one 3-person group. There are actually 10 of those as well. So you have one 5-person group, you have 5 4-person groups, you have 10 3-person groups, you have 10 2-person groups, you have 5 1-person groups, and you have 1 0-person group. So you see that pattern, which you may or may not have seen before. You'll see it a lot in the second semester. Now that I mentioned, so again, this may be above your head, but I'm going to tell you anyway, just so you know. Okay, so let me just give you a little. This is from algebra. So if you have something, this is called a factor, I guess, or something, or it's a, I just really call it, I guess it's a factor. So if you take x plus 1 to the first power, that just means it's just by itself. If you have it to the second power, you take it and you multiply it by itself twice, just like normal exponents work out. So when you multiply this out using FOIL, which you guys should remember to some extent, you get that. And if I look at the coefficients in front of each term, I've got 1, 2, 1, right? 1, comma, 2, comma, 1. It turns out that, or if I use just letters, if I said a plus b squared, that would be a plus b times a plus b. That gives you a squared plus 2a times b plus b squared. So that's FOIL using all letters. And you use the same thing. You take a times a plus b times a plus a times b plus b times b. And then the two middle terms, a times b and b times a, is the same thing, so you get 2 of them, and you get that result. So it's kind of like the coefficients in front are 1, 2, 1, just like you did with something you might remember from algebra. It turns out that if I take a plus b to the 5th power, which is a plus b times a plus b times a plus b times a plus b times a plus b, which you probably haven't done that. I mean, it would take a long time. You have to actually, it's not FOIL, but it's the same kind of idea. You get a big long expression, but a lot of them are going to be the same, and you combine all the ones that are the same, and you have so many of those. And if you multiplied that out, you would get a to the 5th power from a times a times a times a times a. You would have 5 a to the 4th times b plus 10 a cubed b squared plus 10 a squared b cubed plus 5 a times b to the 4th plus b to the 5th. So all that stuff, when you multiply it all out, ends up looking like that. And if you notice the coefficients, they're 1, 5, 10, 10, 5, 1, which is the same number of sets that we ended up here. It's not a coincidence that that happens. Don't worry about that. You know, this is, you don't have to know this. It's just a little extra stuff for you. There's your homework for section 2. It's basically answering questions about whether something's a subset of something else, whether it's what the complement of something is. This one will be due, yeah, you want to do it before, well, you want to do it by Tuesday because that's when the test is. So I would suggest, so even though I'm assigning it Thursday, oh, did I already sign it? Yeah, good. Okay, yeah, I signed it for Tuesday so that you would have it done for the test because you need to know how to do this stuff. Yeah, so I already assigned this. I do remember that now. The other class I forgot to assign it, but yeah, okay. So we're moving on to section 3 now. Since I have already assigned it. There are only 4 sections in chapter 3. Well, we'll be done before we know it. I just didn't want to take another week to take a test. Okay, so section 3 talks about operations with sets. So it's kind of like multiplication, division, addition of subtraction, but with sets instead, not with variables. So the first operation is called an intersection of sets. So the mathematical description, it says the intersection of sets A and B, written A intersect B, which looks like an upside down U, is the set of elements common to both A and B. So that's the written description of what a intersection is. In terms of the mathematical way of describing it, you would read this as A intersect B, which is a set. So when you have two sets and you do an operation between the two sets, you end up with a set. It's like numbers. When you add numbers, you end up with a number, not a letter. Has anybody ever heard of a vector? You know what a vector is? Okay, a vector is something that has a value, but it has a direction as well. And it turns out when you add vectors together, you get a vector. So it's kind of, the operation has to have similar things to operate on, and the result is the same thing that you started with, which is a vector. I mean, in this case, is a set. So it says the intersection of set A and B is or equals the set of all x such that x is an element in A and x is an element of B. So the key thing is the word and. So and if you look at the description, it says common. So common and mean the same thing basically. So remember, this means is an element. Yeah, it's in your book, so you can, let me just see what I have on the next page. Oh, okay, so there we go. I already have that written out, so I don't have to do it again. So here we have two sets. We have set A, which is A, B, C, D, and E. Set B is the letters C, D, and F. So from a subset standpoint, is B a subset of A? You're all busy still writing the set down. So once you've finished writing those down, is B a subset of A? The answer is no, because B has the letter F and A does not have the letter F. So they're not, but they do have some common things. They both have C's and they both have D's. So if I look at doing the intersection operation, if I said, what is A intersect B? The answer would be the set of the letters C and D. Okay, so that's all it is. It's just a new set with the elements of the two sets which are common to each other. So it's just a matter of finding commonality. Okay. So let me give you another, just put another set up here. Let's say I have set C, which is the letters G and H. So if I said, what is A intersect C? What's the answer? Is it 0? Is it? You wouldn't be 0 because that's a number. We're dealing with sets. So what's the name of the set that doesn't have anything in it? I think I heard somebody said no. It's the null set. So the way we would answer this is we would just put either a set with nothing in it, or we would say the null set. So there's no Now you can do this, you can show the operation as a Venn diagram. So let's make up a Venn diagram here. So we're going to have our universal set, which is going to include all the letters from A to H. And let's see what this is going to look like. So we're going to have two circles that overlap like this, and then we're going to have a separate. Well, we don't necessarily. Yeah, we have a separate circle out here. Okay, so the rectangle represents the universal set. This, I'm going to say this is set A, this is set B, this is set C. So the way you would draw this as far as a Venn diagram is this area where these overlap is this intersection. So A intersect B is the letters C and D, so I'm going to go ahead and put those in there. The letter F is in set B, but it's not in set A. And the letters A, B, and E are in set A, but not in set B. And then G and H would be over here. So if there's no intersection or overlap, in terms of Venn diagrams, intersections only happen if there's an overlap. And the overlap represents the letters or the elements that are in both sets. So if I imagined that this circle was not even here, I'd have set A would consist of A, B, C, D, and E. If I imagined that A wasn't there, set B would be the letters C, D, and F. And if I imagined those weren't there at all, then set C would be G and H. And the universal set, which we haven't defined, but we will now, the universal set would be A, B, C, D, E, F, G, H. Okay, let's look at something new here. Let's see. Okay, so that was intersection. The other operation, well, it's not the only. There's one more operation, but the union of sets is where you create a new set which contains all of the elements that are in one set and all of the elements that are in the other set. And if you have any overlap, you just list it one time. So it says the union of sets A and B, written A union B, it's like kind of like a U, but a little bit bigger, is the set of all elements belonging to either A or B. And the way we do it in this set builder notation is we say A union B is equal to the set of all X such that X is an element of set A or an element, X is an element of set B. Notice we're using the word or. So or is kind of an inclusive thing. Did anybody watch the thing last night on TV, the Trump-Clinton thing at all? Yeah. I'm interested. I haven't had a chance to read people's opinions of what was said last night. What's that? Oh, it was called the Commander-in-Chief Forum. And it was a group of veterans that were able to ask questions of the two candidates. They didn't ask them. They had Hillary Clinton first, and they had Donald Trump second. So there was they didn't see each other. I guess they probably sent one off one side and brought the other one on the other side. So they didn't punch each other out. And so Matt Lauer, who's the host of the Today Show, he asked questions, but then the audience got to ask questions. And it was kind of interesting because afterwards they had an analysis on MSNBC with Rachel Maddow. Anybody know who Rachel Maddow is? She's a she's somewhat liberal as far as her opinion, but she's pretty good at being fairly objective when she interviews people. So they were able to ask the people who asked the questions. They asked them, did they answer the questions? And typically it's typical for politicians, they pretty much said no, they didn't answer the questions. So There's some good questions. There's one about sexual assault in the Army. You know, that's a big issue. How you would deal with that. That was for Donald Trump, relating to, you know, how do you combat that? Of course, there was one to do with about, well, this is also for Donald Trump, about if you had a undocumented immigrant who wanted to serve in the Army, what would you feel about that? And do you feel after they served and were honorably discharged, should they get the chance to become a citizen or not? That was a good question. And they had some experts, some military people, and they said that from that perspective, as far as serving for your country, or for your country you would like to be a citizen in, they pretty much everybody said they think that's a good idea. That's another interesting thing here. So you don't know this, but well, I told you I was from England, and when you come to the United States legally, you get what's called a green card. And so even though I came as the child of the parents who came, the children have green cards. And what that does is allows you to work in the United States. It's not a work visa. It's basically you can do any job that's not handling classified information or something like that. So I had a green card, and but if there was a draft, I could be drafted. So you don't get out of you don't get out of the draft because you're not a citizen. As long as you are a permanent resident of the United States, whether permanent legal resident of the United States, which is of course citizens, and also green card holders, that you can be drafted into the Army. Now I don't know if the country you come from, if you're living somewhere else, if they'll draft, you know, if you like, you're double in jeopardy here, you can get drafted into both armies or whatever it was. So you know, a lot of people think, oh, if I don't become a citizen, they can't draft me for the Army. Well, that's not true. So the only disadvantage of there's not that many disadvantages for being a citizen compared to being a green card holder. You get to vote, which is good, which I always do. So. Okay, back to unions. So let's look at let's just look at the same example, and maybe that's what I have on the next page. No, I don't. Okay. So let me pull my picture over here so I don't have to rewrite those sets. Okay, so here we have the sets, and this was the operation of intersections. So we had A intersect B. So in this case, I'll do it over here. When you do the operation of a union, you basically start listing the elements that are in the first set, and when you get to one that's in the second set, you just keep writing it down. So I've got A, B, I've got C in both of them, so I write it down once. I've got D in both of them, so I've got both. And then E is in the first one but not in the second one, so I list that. And then I also list F. So these are common, not common, but they are, it's this either or kind of thing. These elements are in either set A or set B. They don't have to be in both, that's an intersection, but if they're in one or the other. So if I did A union C, then I would have A, comma B, comma C, comma D, comma E, comma G, comma H. Because what I've done is I've gone A, B, C, D, E. I go to this one. I don't have any that are common, so I just keep writing GH. So that's union. The only time you could ever get a union or get a null set from a union is if you started with two null sets, and then the union of two null sets would be null. But you're always, in the case of unions, you're always making the result is always bigger than the original, equal to or bigger than the original two sets. When you're doing intersection, the answer wherever it is here is right here is either smaller, equal or smaller than the original set. Okay, so that's a union. Then we have differences. So the difference of sets A and B is written A minus B, and is the set of all elements belonging to set A and not to set B. So it's written A minus B is equal to the set of all X, such that X is an element in set B, but not in set A, but not in set B. So while you're thinking about that or writing it down, I'm going to do a Venn diagram to show you what this looks like. And then we'll do this. So we'll start with the Venn diagram this time, and we'll move to the other one. So here's our universal set. Here's our sets A and B. There's some overlap. And let's put some numbers instead of letters just to be different. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's the Venn diagram. So let's talk, before we talk about A minus B, let's talk about this. This is set A. I didn't write it down, but this is set B. So set A would be 1, 2, 3, 4, 5, 6. That would be set A. Set B would be 3, 6, 7, 8, 9. Everything that's inside the second circle. A intersect B would be the set of the numbers 3 and 6. The union would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So let's write all that down, what I just said, on a separate page. So let me, oops, didn't want to do that. I'm just going to make this thing a little bit bigger. So that's not what I wanted to do. Okay, so based on the Venn diagram that I just made up, this is set A, this is set B. So set A consists of the numbers 1, 2, 3, 4, 5, 6. Set B consists of the set 3, 6, 7, 8, 9. The universal set would consist of 1, 2, 3, 4, well, I'm also going to do one less thing. I'm going to put a 10 out here, okay, just to be different. So, so the universal set would include all the numbers that are in the circles plus the number 10, which is in neither A or B. So that's 6, 7, 8, 9, 10. So the universal set consists of all the numbers from 1 to 10. Okay, now let's do some operations. Okay. So if you take A intersect B, you would look here. You could do it from the sets by looking for things that are common, and I look here and I see 3 and 3 are both in sets A and B, and I see 6 and 6. So looking at in terms of listing of the sets, I would say 3 and 6, and visually I would look over here at the Venn diagram and I would say it's 3, 6. Okay. If I looked at the union of A and B, again visually it's everything that I see listed inside of both of these. This one, we don't double this up, so we just include this one time. So the union would be all numbers between 1 and 9, including 9 and 1. So all inclusive. It's an all-inclusive deal. Has anybody ever been on a cruise? Yeah. Do you like it? Yeah. Yeah, I've never been on a cruise. 2 things bother me about a cruise. One is that word all-inclusive, I don't trust them. So I'd like to pay the money and know that I'm not going to have to pay any more for anything. But there's always extra. Isn't there some extra things you get, like excursions? You got to go pay for excursions. You don't have to. Well, you don't have to go on excursions, but then you're stuck on the boat, right? Are there enough? You just. Okay. The other one is I know I'd eat way too much. Like I have no self-control for buffets, so that would be a bad thing. Okay. That was an interest. So talking about cruises, they had this thing about the 10 most dangerous places that you can get off on a cruise ship. So I was watching that, and number 2, I mean, they had Egypt, which, okay, I expect that, Turkey, places where there's terrorism, possible terrorism. Number 2 was St. Thomas in the U.S. Virgin Islands, which that's the one place I have been, not on a cruise, but we've gone to St. John, which is right next to St. Thomas, and yeah, it's dangerous, but I wouldn't have thought it was number 2, worse than some of these other places. But anyway, that was okay. So that's the union. So then the subtraction question. So A minus B. So what A minus B? Visually, it's this little crescent. So it's everything. It says it's A minus B are the elements in set A, but that are in set A, but not in set B. So these two are in set A and set B. So you have to remove those out. So the set in this case A minus B, using this example, would be 1, 2, 4, and 5. Visually, it's easy to see. You just say, here's A, there's B, take them out of there, I can look at it. From a looking up there, what you would do is you look for the ones that are common, which are 3 and 6, and take those out. So it's almost like you look for the intersection, the stuff that's in the intersection, take those out of the original set. So if you take B minus A, unlike math, regular math, B minus A is different than A minus B. So B minus A would be, let's see if you can figure that one out. So, Brooke, yes, did you do that based on the figure or based on looking at those sets? Since I took them off, you can't see them now, but yeah, you were looking at the drawing. So yeah, visually it's easy. It's 7, 8, 9. So, and it turns out there are some what we call identities, which are just things that are always true, and that relate these kinds of operations to those kinds of operations, which we'll see in a little bit. Okay, let's just save this for a second. Okay, yeah. The final operation is this one, which is called the complement. And I don't have any words written out for it. There's probably some in the book. Let me see if I can think of what to write down here. We actually talked about this already in the first section, I think. We used the symbol prime to show complement. Let me just do it from a Venn diagram standpoint. So here's my universal set. Here's my set A. We're only looking at set A. So this is U, this is A, and this is going to be A, B, D, C, F, G. So set A is everything that's in the circle. The complement of A, which is A prime, is everything that's not in set A. So it's everything that's outside. So the set is inside, the complement is outside. And the operation is just this symbol. So it's not like you have the complement is always just the complement of a single set. Well, actually, you could you can use parentheses like you do in algebra to do an operation, and then you can take the complement of that operation. We'll talk about that in a second. So, but for right now, if you have parentheses to do a operation first and then do the complement of the operation, the complement, the operation will give you a set, and that set you take the complement of. It may not have a official designation like that set C or whatever, but it's anyway. We'll get to it in a second. So now we're going to do some more examples. So these are just a different universal. It's pretty close to what I had before. So you've got the universal set, which is the letters A through G. You've got set X, which is A, C, G, and E, which is kind of like the odd letters. You have set Y, which is the letters A, B, and C. And you have set Z, which is B, C, D, E, and F. And what they do is they want you to perform the operations. And what that means is that the answer is a set which contains the appropriate elements associated with the operation. So here we have, actually before we do that one, let me do a simpler one. This might be number 7 on the test, but I'm just going to put it in there because I think it makes more sense. So this is N1 again. If I said, what is X intersect Y? It's a set. And what does intersection mean? Is it common or is it either or? Which one goes with intersection? Common. So what are the elements that are common between set X and set Y? A and C, yeah. So we're just looking at those. Make sure everybody does that, agrees with that. But what you do is you look back and forth between the two sets. And you can use your fingers if you need to. I find people, I use my wife as an example because she's not a math person. And she's smart, but there are things like this that I see on the computer that I'm, I seem to, because I'm a math person, I see that connection more quickly. So if you don't see it as quickly, it doesn't mean anything. It just means you got to figure out a strategy so that you can answer the question. So anyway, so I'm doing it visually. I'm just looking back and forth and looking at it. So you see A is in set A. Letter A is in both sets. Letter B is only in set Y, but not in set X. And the smaller set's probably the easiest one to compare because you got less elements. And then you see the C. So there's a C common. So the intersection of sets X and Y are the letters A and C. It's kind of like, has anybody ever used Access database? A database? Like a lot of times when you search a database, you're trying to find, let me find this. Lowe's refrigerators. Okay, let me.
So this discussion board assignment is we're talking about sets, and in computer programming language they have different names, but a lot of times they're called arrays. So I want you to just find a reference for arrays, and so what I want you to search for is Java programming. I think that's spelled wrong. 2 M's. And then put arrays in. And just choose one of the first articles. And just read that and kind of give me a 2-sentence summary of what arrays are. Okay.
Store that. Okay. I'm not promoting anybody's refrigerator. That's one. I listen to the English BBC, which is like state-run, and they have a rule that they can't mention brand names because they don't want to be promoting. So they'll say some popular appliance that rhymes with something or other. It's just, so when you go looking for a refrigerator, you see these things on the side, which are different characteristics. And what you're really looking for there, you're looking for intersection of various things. You're looking for certain characteristics that you want, whether you want stainless steel, whether you want, in this case, the width of the cabinet and all those kinds of things. So you're looking for commonality. So all these, searching through these databases of all these refrigerators which have all these characteristics, and you're trying to find the ones that have the characteristics that you're interested in to narrow it down, or you go crazy trying to look at all the choices. So it's kind of like that. I don't know, it was better when there weren't many choices. You go into, there are 3 washing machines. It's easier to decide what you wanted to do. Okay. So so then we have X union Y. So that one is where we're looking for, list all the elements that are in set X and all the elements in set Y. So again, you could list all these and list all those, and then you eliminate the ones that are common. Let's just use that strategy just to show you that's one way of doing it if you wanted to. So if you listed the elements in set X and the elements in set Y, you would get that. But then you'd say, well, set, I don't have duplicates, so I'm going to remove the duplicates, and then I'm going to simplify it. So you get A, comma, E, comma, G, comma, B, comma, C. And then you could put them in alphabetical order if you wanted to. Or you can just look at them and say, okay, since these are usually in alphabetical order, I just go through the alphabet. A, B, C. There's no D, so I leave that out. So, and I must have missed one here. Oh, I forgot. Oh, there's C. Yeah, A, B. That's why alphabetical order is good. A, B, C. When I get to D, I see that it's in neither one, so I don't list it. E is in this one. F is in neither one, so I'll leave that out. And I put G. So either way, I don't know whether you have any problems doing that. If things are in alphabetical order, it's probably easier to just kind of go through the alphabet and write down the ones that are in the 2 sets. Okay, what else have we got here? X union with the universal set. Well, the universal set includes everything, so that's kind of a no-brainer. That is just you could say it's the universal set. But we wouldn't normally do that. We would list out everything. So what they're looking for is not a number. This would be the only case that probably could get away with that. But because X, everything in X is in the universal set, by definition of the universal set, you would just write down the universal set as being that. If I said, what is X intersect the universal set, that actually would just be equal to X, because all the other stuff, the intersection, we've got everything in the universal set that's in X, so we know everything here is going to be there, and the ones that are not in X we don't list because they're not common. So if we did the intersection of X with the universal set, it would just end up being the set X. Okay, so those are easy. Now they get a little harder. So how much time we got left here? Okay, 7 minutes. So we'll get through maybe 1 or 2. So as I was saying earlier, if you have parentheses, what you do is you do that operation first, just like you would do in algebra. So what we're going to do is we're going to create a set that's the result of the intersection of Y and Z. We could give that a name. maybe that would help. But what I would do is, you can't do all this in just at one time. People try to do it, it's not going to work. So what you would do is you would first do the operation that's in parentheses first. So then we look over here and we say, okay, what's the intersection of y and z? So I'll ask you guys to figure that one out. So top row, what's the intersection of y and z? What are the elements in the set that's the intersection? So it's the letters that are common between y, set y, and set z. Yeah, BC. Good. So we write that down. So then what we can do is we can take X union this result. So I'm going to actually put the actual set things in, because if you start trying to do this without including the intermediate stuff, you're going to be in trouble. Okay, so first row, what is the union of X and the set that includes B and C? So let me put a parenthesis and somebody can tell me what they are, and we'll see if you're right or not. A, B, C, E, and G. Okay, so X consists of 4 elements, and this consists of 2 elements. B is not in X, but it is in the union. So you add that. What ends up, the union ends up adding B to the original set. Okay, so that's exactly what you do. So what we would do here is we would, well, this one. So we're already moving on to more difficult stuff. The way you would do this is you would do it in the steps, is you'd find the complement of X first. So we're going to get some set associated with the complement of X. Then, secondly, we would take Z union the complement of X, which I've already figured out right here, which we'll write out in a second once we get it. So that's the third thing we do. The second thing we do. Then the third thing we do is we have to take the complement of this thing, which we have previously. So we're going to take the complement of this, which is everything that's in the universal set, but not in that. And then finally, I don't know if I could slide this down or if they're all connected. Oh, good. The fourth step is then we would do the whole thing. Now we have Z union X complement, which we have previously, and we would then do that with the intersection of Y. And then we finally get our answer. So let me do it for you and show you how it works. So we'd go over here to X, and we'd say what elements are in the universal set but not in X. Well, notice I go A, C, E, G, so the complement would be B, D, F. B, D, F. So the complement is everything that's in the universal set but not in set X. Now what I'm going to do is I'm going to say Z union, and I'm going to write out B, D, F, which is the complement. So I'm going to do this thing next. So now you can look over there. If you take Z union B, D, F, you're going to have B, D. Well, in that case, Z already has B, D, and F. So that turns out just to be, just Z, which is B, C, D, E, F. So the union didn't actually make it any bigger. Am I doing this right so far? I think I am. Okay, now I take that and I take the complement. So I'm going to take the set B, C, D, E, F, and I'm going to take the complement of that. So again, the complement of a set is the elements that are in the universal set but not in the set. So that is going to, the only 2 elements that are in the universal set that are not in this are A, and G. So that is the complement of this thing. And then finally, let me move this thing down a little bit. Finally, I take this set, A, comma, G, and I have the intersection with Y. So I take this and I look up here to Y, and this is intersection, so that's what terms are common. The only term that's common between Y and this set is the letter A. So the final answer is A. Okay, so it's not that hard. It's not any harder than just doing them separately. It's just keeping track of which operations you do first and doing them in the correct order. And those are probably the hardest thing we have to do. Well, no, it's not. We have some nice stuff in section 3 as well, but I was just making sure I got the right answer. So what have I got? It's A. It's 21. Let's see, what do I get? 21. It's A. I got the right answer. Yay! Okay, so we'll do some more of these on next Thursday. Remember, the test is on Tuesday. Let's see who. Make sure I get Carter. There's Carter. So for you guys online, just to make sure you're paying attention here, let's see what. Send me a little note in the chat window that says I'm awake or something like that. So we'll see if you are. So Carter's apparently awake because she's got a little thing. We'll give the other guys a second here. So remember, if you're online, I'll do that every once in a while just to see. I'll ask a question or I'll ask if you're awake. And if you don't respond, then you don't get full credit for attending. So that's, I'll leave it on for a few minutes to see if sometimes the connection is slow, and at least that's what the people say.